So everybody, let's begin. So we're going to talk about compositional statistics and complex heat maps today and how this relates to environmental public health trends. So what are compositional approaches? Well, there are many phenomena in the world that we can consider to be compositional. They are geospatial, environmental, molecular, and there are several other examples across multiple different sciences. The key thing is that these are data which are proportional. So they are either summing to a whole or part of a whole, and they're represented as data as either percentages or as parts per million or parts per billion, but they can appear in other forms too. So the data, generally speaking, are under a zero-sum constraint. And what this means is that the numbers that you gather in this type of data must be considered as having compositional relationships, so relative information to each other. And the reason we do this is, and the reason this is important, is because otherwise we may come to misleading interpretations, often caused by co-correlations or co-occurrences that we might see amongst those compositions. Okay, so compositional transformation. So this is one of the main ways that we target this type of research. So there's a classic example of a composition, which is a pie chart, and there are a variety of transformations available. So there is the centered log ratio, which retains the geometry of the original data. We have the isomorphic log ratio transformation, which is an orthonormal transformation and allows us to observe subcompositions, so relationships between different slices of pie. But others exist. We will be talking about the CLR and the ILR today, but there are others. There is the ALR, the PWLR, and there's also a variety of compositional techniques such as the Salbel algorithm and robust PCA analysis. Okay, so what are the main challenges? The main challenge is we often have a very large number of variables. We're often making observations based on these compositional balances. And we are then forced into a position we have to interpret them, and the correlations between compositions have to be considered in these interpretations. And there are several ways of doing this, complex heat maps being one approach. So next question, what is a complex heat map? Generally speaking, it can be any one of the sorts of diagrams that you might see there, aside from the ones in the middle, but essentially it is a dendrogram showing multivariate relationships coupled with a heat map of some kind. And the heat map is often created using something like a Spearman's correlation, but it may also be something like ranks or scales. The heat map will show both positive, neutral, and negative trends. Okay, so these are two examples. So one here is from a paper on soil geochemistry, and you can see the elements in that soil there. And on the other one accompanying it is from another study which was looking at trends in chronic kidney disease. And you can see there that there are different symptoms and different markers of chronic kidney disease and how they relate to each other this is being done using a complex heat map as the graphic tool. So how does this apply to what we're doing today? Well, we're going to be talking about data nested in the SOAs of Northern Ireland. So these are these lovely little polygons. These are polygons created with population density in mind. And we're going to be talking about some health data and some soil geochemical data. Okay, so the data that we have. So we have data which was part of the Northern Ireland multiple deprivation measures from 2017, published 2019. Broadly speaking, we're talking about a number of health variables. So we're talking about standardized physical health, we're talking about cancer, we're talking about emergency admissions, we're talking about singleton births with low birth weight, children's dental extractions, multiple prescriptions, and standardized ratio of people with long-term health problems, excluding mental health. Now, obviously, I've created shorter approximations of these. We don't necessarily need to worry about them, but we will be talking about two in specific. But if anybody has any more questions related to these at the end, please do let me know. So what's our soil data? So our soil data comes from TELUS, which is a part of the, which is a geochemical and geophysical survey, which is part of GSNI. I have done two transformations here using summarizing. I've transformed the data using the CLR transformation, and then I've used that CLR transformation to inform what the subcomposition should be, which is how I've decided on what the ILR transformation pairs should be. And then essentially what I have done is I have then plotted those data as points, and then from those points I've extracted that information and basically calculated the geometric means of the elements within all those compositional balances within the SOAs. So that's basically what you're seeing here. So the elements that we're looking at, we've got zinc, we've got cadmium, we've got lead, we've got molybdenum, we've got aluminium and nickel, among a few others. And then, as you can see from the diagram from the CLR, on the ILR, is that all that you're seeing there is that wherever two pairs of elements occur in the CLR plot, those pairs have become a subcomposition, which you can see in the ILR plot. So if you notice at the bottom there, we have manganese and copper, we have chromium and manganese, and then at the bottom there, we've got a balance for chromium and manganese. So that's essentially what we're looking at. There's a lot of information here, a lot going on. But essentially, we're looking at basically a data reduction technique. Okay, so what happens? Well, we take those back. Here we've got the, we take those balances and we put the health data in with them. And essentially, this is the CLR map with those health variables included. It's the geometric means with remembering this with the soils and summarized within the SOAs. And essentially, we have two distinct soil groups. One of those is more geogenic, one of those is slightly more anthropogenic, but that's not what we need to concern ourselves with today. What I want to draw your attention to is that the soils and the health variables do correspond with each other. That's what we would expect to see, broadly speaking. They've got more in common. Soil geochemistry has more in common with itself than it does with health variables. That's what we would expect to see. But importantly, what we can see is we can see these areas of red along here where we have cancer and other variables corresponding. So we've got the emergency admission and we've got rate of cancer here, and they're corresponding with some of these balances here. So, and we will discuss that in a little bit more detail on the next few slides. So geometric means, let me just move that over this way. There we are. Okay, so geometric means, so we've got the groupings here a little bit less distinct when used the ILR. That's to be expected. We've simplified the data in a way by looking at the subcompositions rather than preserving the original geometry of the table or the data set. But what we can see here, and we've also, in terms of their positioning in the plot, they flip around. But essentially what we're seeing here is something very similar. We've got the health variables coming together, the soil variables coming together. We've still got those two soil groups coming out, but what we're starting to see is these correlations here. So what we can do is we can use these correlations to inform choices that we might make in the next phase of data analysis. So this is a very good way of looking at lots of data variables together and having a more simplified approach for judging what might be statistically relevant. So so what I have done here is I have taken the ILR balances for thorium and rubidium, chromium and manganese, and then tin and lead. And we're looking at them in relation to the rate of cancer. So broadly speaking, we can see that we've got some relatively consistent positive correlations, but there's nothing here above 0.5. We've got positive trend lines, but we also have a lot of data grouped to the left-hand side of these trends, and we've also got a lot of dispersion around those trends. So we've got a relationship, but it's proximal. It's not the sort of nestedness around a line that we would expect if we were noting a really, really strong, noticeable trend. But what we can do is we can take this information and we can go further with our analysis. So here, all I have done is a multiple regression with the rate of cancer against the balances that we were talking about before. And essentially what comes out is that we do get significances. So we can see that there is a relationship, at least in a potentially causal relationship, between those ILR balances and the rate of cancer in the SOAs across the whole of Northern Ireland, or in the SOAs that we have data for. So that's what through this approach, we've been able to get to a place where we can see that. But what's really important here and what needs to be thought about is that although that we can see we've got a significant result out the other end, and although we can potentially infer causal relationships, we've got very low R-squared values, which from a statistical point of view means that there's a huge amount of variance that we haven't been able to account for. There are multiple factors, and obviously in a health context, this makes sense. We know this, that these things are there's often multiple causes to a health outcome. So how does this relate to current research? So
Okay, Shay, sorry, just 1 minute, if that's okay.
Oh, okay, sorry. So I'm a part of the space project. So obviously that type of approach you saw is is the sort of standardized analysis that I would normally do if I was investigating a relationship between soils and a health outcome in humans or another organism. But as part of space, we're trying to account for a lot more. So I would normally worry about environmental exposure, but we're also worried about socioeconomic effects, lifestyle and location, and we're interested in noticing that in terms of somebody's long-term health outcomes, and especially cognitive health. So that's what we're worrying about in space, and that's what we're trying to do, and we're trying to take account of that multiplicity of variation and variables together to try and get to the cause of what is really going on in the spatial context. And this is the lovely team that I work with, and our funders, obviously. And any questions?